All right, so now we're going to talk about immersions and submersions. So this is going to be a very efficient way of constructing it's like submanifolds and quotient manifolds. Okay, so let's say we have a map F from M1 to M2, right? Be a differentiable function. From a manifold M1 of dimension D1 and to a manifold M2 of dimension D2. Okay, so if you have a point x in M1, right, then the rank of F at x, right, is the dimension of the range of the linearization, the f hat. So it's linearization of the coordinate representation, right? Which is a map from RD1 to RD2. Okay, so where f hat is the coordinate representation of f. About the point x. And d f hat, right, at this point is the differential of f hat at the point phi 1 of x. Okay, and the point is that the notion of rank is again independent of the choice of coordinate chart, right? Okay. All right. So, so now we can talk about this idea of immersions and submersions. Okay. So the function f is called an immersion right? If its rank is equal to D1, at each point in the domain, and then by necessity this means that D1 is less than or equal to D2. Okay. So if its rank is equal to D2, at each point in its domain, then in particular this means that D2, well D2 is greater than equal, whatever. Sorry. So that's D1 is greater than equal to D2. Okay. Then it is called a submersion. Okay. All right. So these are the sort of the definitions. It's like of the immersion and submersion, and they're defined in terms of this rank, and the rank is defined in terms of the essentially the linearization of the coordinate representative of the function f, and basically the dimension of the range, right? Okay. So so let's see what you can do with these things. So the function f is an immersion if and only if around each point of its domain it emits a coordinate representation that is the canonical immersion. Okay, which is that it maps coordinates u1 to ud1 into u1 into ud1 and then a bunch of zeros after that. Okay. And again, it's like, if you recall, it's like in an immersion, d1 is less than or equal to d2, right? So if it happens to be that d1 is equal to d2, then obviously there's none of these trailing zeros. Okay, but otherwise it's like there's some sort of local coordinates where, you know, it's like this is, you have this kind of coordinate representation of the function f. Okay, and then the function f is a submersion. Right, if and only if around each point of its domain it emits a canonical immersion, canonical submersion. Okay, which is basically that you know, you have u1 to ud1 again, and it maps to u1 to ud2, right? So d here again, d1 is greater than or equal to d2, so it's quite possible that you just truncate a few of the entries in the coordinate system. So it emits this as a coordinate representation. Okay, so these are, of course, it's like the most sort of natural things to have, right? One of which is that, you know, you have in principle, a low-dimensional manifold. It's like, and you include it into a higher dimensional manifold by sort of augmenting the coordinate entries. It's like with a bunch of zeros, or you have, in principle, possibly a larger dimensional manifold where you include it into a smaller dimensional manifold by just dropping a few of the coordinate entries. Okay. So again, these are the canonical immersions and the canonical submersions. Okay, and then we can say something about the regularity of these points. Right, the point, let's say y in M2, right, is called a regular value. Of f if the rank of f is d2 for every point x in the preimage of y. Okay, so again, it's like this is this notion of immersions and submersions, and we're going to see that that's going to be useful. It's like in showing that various objects are manifolds. So let me just stop here for a second.